Okay, good afternoon, Seattle. I'm Stephanie Tzeng, and I am a data scientist at AppNexus.
I'm Sal Rinchiera. I'm an optimization engineer at AppNexus.
And today we're going to be talking to you about a redesigned algorithm on our platform. So it's 3:47 right now on a Saturday afternoon, so if you're here, you must really love online advertising or your boss is sitting next to you. Let me start out just by doing a questionnaire because this is just like, I've been to a couple of these sessions, it keeps happening. So how many of you have heard of the internet? Great. Oh, not everyone. Wow. And how many of you have seen online ads before? Nice, nice. How many of you have clicked or bought something off an ad? Oh, yeah, I was expecting not that many hands, but there's a couple. So what we're trying to do is increase that number by improving user engagement and serving better content on the internet. So what is online advertising? Let's say that you're business cat and you're a user on the internet. You really like litter boxes, so you're going to go on litterboxes.com and just to see what's the latest and greatest developments on litter boxes. So the first thing is that the web page starts to load, and there are ad slots. Before the ad slots actually populate with content and load, there are auctions that are firing off for every single one of these slots. So what's happening is that different advertisers are bidding values into this auction, and they're trying to compete for the attention of business cats. So what they're going to do is just bid some value, and in this case, the one with the highest is buy one, get one laser pointers. And they're trying to get business cat to click and buy laser pointers. So if you step back, there's actually millions of auctions happening every second, and there's thousands of publishers and advertisers all trying to interact in this space. So now I'm going to hand it over to Sal to explain how AppNexus fits into this.
Great. So AppNexus is the platform that connects the advertisers and buyers. Our technology has implemented this auction house or ad exchange where advertisers can bid dollar amounts to show users ads and where websites can route all of their ad traffic so that they can monetize their inventory. Since it's not a trivial technological pursuit to participate on the ad exchange, we also offer tools for advertisers where they can set up their ad campaigns and have AppNexus do the actual bidding on their behalf. Similarly, we have a suite of tools for publishers to do all the sorts of fancy analysis and revenue maximizing for their inventory that you imagine they would want. So to give you an idea of the scale at which AppNexus operates, we conduct about 120 billion plus auctions per day. From those auctions, we serve 44 billion ads, which accounts for about 170 plus terabytes of data. So to put that number in perspective, core and tool from Alpha, that's enough data to fill the human brain capacity in 12 days. It's also enough data that if you were to print it on pieces of paper, it would account for 700 billion pages of printed information per day. If you stacked all of those pieces of paper on top of each other, it would stretch 40,000 miles of printed material, which is enough to reach the moon in 6.5 days. Unfortunately, it would also cost you $273 billion in printing costs. So poor big data. He's always the butt of the jokes. Next slide, please. Thanks. All right, so here's a little diagram of how we facilitate this at AppNexus at a very high level. So business cat visits an ad, sends the ad request to the AppNexus impression bus. Called the impression bus because it's responsible for routing requests to other parts of our AppNexus platform, other subsystems. The most important of which is the AppNexus bidder, which is responsible for taking that bid request, responsible for taking that impression, the ad request, and returning a bid value, which is a dollar amount, and the ad, which the bidder or the advertiser is going to display to business cat. So simultaneously, the impression bus is also routing these impression requests to other bidders who are also returning dollar amounts and ads. So whichever dollar amount's the highest, that's which ad gets shown to business cat. So the AppNexus bidder, besides for returning an ad request, also logs a piece of information about the auction and about the bids into HDFS, which is our Hadoop distributed file system, which contains all of the raw log data on the AppNexus platform. From there, it's processed by our data pipeline, which does basically aggregations to store it in a consumable format for different processes on the AppNexus platform. We use a Vertica database, mostly to store this aggregated information. And then the data science and optimization portion of AppNexus, this is where we fit in here. So we consume from the Vertica database, do a bunch of different calculations on the aggregated data, for a bunch of different purposes. Talk about one purpose today, but we do a ton of computation and store the results of this computation into a MySQL database, where it's then written by the AppNexus bidder to influence future bids. So this is the feedback loop over here. As far as the optimization and data science teams are concerned, the majority of what we do, but not all of it, but the majority is all offline learning, offline computation, which really lets us take advantage of high-level programming languages like Python, and lets us sort of ignore the problems of, how exactly can we read in and process billions of requests a second. We can sort of not worry about that and really worry about just implementing the business logic to iterate fast. Great. So today we're going to talk about a very specific problem of the data science and optimization teams. So we're going to zoom in a little more into performance buying. Performance buying is a very specific type of transaction that happens on the AppNexus exchange. It's when a website will only get paid if a user engages with an ad. For example, a user clicks on an ad, or a user makes a purchase based off of an ad. So on the flip side, the advertiser will only pay out when this action occurs. So here's a little example where Bogo Laser Pointer says to litterboxes.com, I'll give you $10 if somebody clicks on my ad. Litterboxes.com only sees that offer, so he says, sure, why not? But once we introduce different advertisers into the ecosystem, things become a little more complicated. You have all of these offers which the advertisers are pitching to litterboxes.com. For example, $100 for a purchase, or I'll give you $7 for a click. So it's not as simple as choosing the highest dollar amount, because as you can imagine, not all of these offers are created equal. The probability of purchasing a car based on an ad may not be as likely as clicking on you want a free iPad app. Maybe it is, I don't know. So in a very ideal world where AppNexus is this omniscient being, we would know exactly which of these offers events happened. So we would know exactly when a user would purchase an event based on an ad. Unfortunately, we're not this all-knowing being, so we can't do that. The next best case scenario is if we knew the probability for which an event happened. If we knew the probability, for example, that a click happened, and we knew the probability was 10%, and we knew that the value, the offer amount for that click was $10, we could do a simple calculation to calculate the expected value of the view or impression by saying $10 times 10% is $1. And if $1 is the highest offer amount, or the highest translated offer amount, then we would choose that offer to display to the publisher or the website. So this makes sense when we have enough data to do this computation. We just get the number of clicks divided by the number of impressions for some offer website combination. Unfortunately, it becomes a much more difficult problem when we don't have any data and we can't make this computation. So Stephanie's going to talk to you about what we do in this situation. Stephanie?
Thanks, Sal. So nice. All right, so before I actually talk about having data or no data, I'm going to talk a little bit about just how important it is to have that one rare event. So in this case, we're talking about a click. The probability of click, as said before, is really important for us to know what the expected value of the offer is. So if you look at, if you have no clicks, but you have some other data, because we're dealing with probabilities here, it just doesn't tell us anything. So 0 out of 10 impressions, or 0 out of 10,000 impressions, there's 0 is the same thing as 0. But if you get one click, then you're actually getting some kind of probability that we're getting somewhere. So let me delve a little bit more into the data and no data problem. If you can think of this as a classic exploit and explore problem. If you have data, we call this an optimized state. That's when we have a real probability, we're pretty confident in it. And the purpose of this is to go out and just get revenue for the publisher or the website. The other state is the learn state. That's the exploration state. We don't have any probability, or we just don't have that much data. And so in this case, we're actually buying impressions to accumulate information. So the seller or their website can say like 95% of its impressions are going to optimize, whereas the 5% is going to learn. So how do we estimate this initial probability for no data? So in the old scheme, what we did was we computed some kind of prediction for every single offer and website combination. And we would update the model as we started to get data. The problem is that we're storing all of this in memory, so every single combination is just a lot of information. And the other problem is that elaborate probability prediction schemes are actually not necessarily that accurate, and you end up collecting data like all of these impressions for every single offer. So you're slowly getting impressions, but not necessarily the clicks. So let me dive a little bit in detail for what might happen for one website. So in our bidder memory, we're storing valuations for all the offers. So it doesn't really make sense that we're still storing it for Justin Bieber fanny packs when it's like this low. And so all of these ellipses obviously mean there's stuff in the middle. So why do we continue doing this? So the solution is what we call the quick test approach. And in this case, it's for offers. But you can actually extend this same algorithm for different use cases. So our hypothesis is that for information gathering, it is more cost effective to test out what we call enough impressions for a concentrated number of offers than buying impressions for every single offer based off of a flawed prediction. So as you recall, the click is the most important thing. It holds the key to most of your information. So we're going to use that click as a classifier. So if you have a click, we're going to say that's good. If there's no click, then that's bad. Okay, so what's enough impressions? I'm going to go into a little bit of math here. N impressions is the minimal amount of impressions you need to deem that an offer is bad, even though no clicks have happened. So first thing you do is you calculate a desired probability. So P naught is equal to this equation that uses an average revenue for the seller and a goal, which is in our previous example is $10 per click. So now you have a baseline. Then there's an actual p-value, which is your actual click-through rate for the offer and website. So what you do is you calculate based off of this equation here. So I'm going to step through this. It's the probability that the real conversion rate is greater than P naught. That means the offer is good, given that no clicks have happened and any impressions have elapsed. You set that less than or equal to this lambda factor, which is a false positive rate, and I'm going to go into more detail about that. So this is a conditional probability, so clearly we use Bayes' theorem. You rewrite it like this, and then we can finally rewrite it in this format here. This is Bayes' theorem. And 1 minus p to the n is using the binomial distribution because every single impression either goes to a click or no click. And since there have been no events of success, it's your probability of failures to the nth power, and you pick some kind of underlying distribution for your prior, which is h of p, and we can compute n with this. All right, so you might be wondering what lambda means. So the relationship between lambda and n is this. If you have not that many impressions, you aren't very sure what that means. It could mean that the offer is good, so your false negative rate is really high. If you want to lower your false negative rate, you can just continue to increase the number of impressions that you're testing. But it doesn't really make sense to test like infinite impressions because then you're just wasting a lot of money. But that could mean that you have no false negatives. So what you end up doing is you pick some kind of low false negative rate, and then you can solve this equation for n. And then you stop buying there. Okay, now let's talk about pregnancy tests. So if you are taking a pregnancy test, you want to see you want to see true positives, but you don't want to see false positives. So the same way here, that's what an ROC curve kind of is. So what you want to see is what the ideal place is, and ideally for pregnancy tests, you want to be right here. So what you do in this situation is you look at your data and you try out all these different lambda values. So you're trying to be as close as possible to ideal, but we aren't really there. But you just want to pick some place on this curve, and if you're over here, you're probably wasting a lot of impressions. So you just have to, it's kind of like your own use case, whatever you think is most appropriate for you. So here's just a state diagram of what the offer looks like. First, it goes into an eligible state. Then it starts testing. It tests for n impressions. And if it gets a click, it passes. If it doesn't, it fails. Okay, so let me talk about the implementation of this. There are 3 steps. The first is a rank. So what you do is, based off of your predicted revenue, this is a little bit like doing the probability prediction, but it's more lenient towards being not as accurate. Like, you don't have to be as accurate here. So you rank your offers based off of historical information and some kind of prediction. The second step is you select a top number of offers. So this is a pretty important part, because the hypothesis was saying, don't look at everything, only look at a small amount of offers at a time so you can test it fully. So in this case, what you do is you look at the average number of impressions that was elapsed over, like, let's say 7 days. And if you want the offers to test in a day, you can use this fancy thing called division, and you can figure out the number of offers. All right. The last step is the quick test, which I already went over. So this is still the same number of offers that we were talking about earlier. So during those n impressions per offer, then if it passes, it goes into the optimized state. And if it fails, it goes into this horrible place called adhel. It doesn't actually use this. So let me go into a little bit of the results. As I said before, there's too much information in memory right now, so we wanted to reduce the number of objects testing at a time, and also by doing that, you're just a lot more efficient. So this purple line here is when we turned on the algorithm, and then you see the number of objects testing at a time has decreased dramatically. In the next slide, just shows that the blue line is the average revenue per 1,000 impressions. And after we turn on the feature, we started to see a lot of better results. Now we'll talk about the engineering part of this.
All right, thanks, Stephanie. It's time to put the pie in PyData. All right, I'm done. The talk's over. Just kidding. All right, so if you recall, this is the state diagram. This is the implementation of offer quick test as we sort of see it on the engineering side. We want these offers to go into start off in an eligible state, then go into a testing state where they're later either put into a passed or failed state. So this by itself doesn't seem like a terribly challenging problem. But what makes it complicated is the scale at which we do this. So we're talking about websites, or we're talking about offers serving on websites. And as you can imagine, there are tons of offers, tons of advertisers with tons of offers, and tons of websites on which these offers can serve. So if you have such a large combination of things, then it becomes much more difficult to do this state transition. This is a diagram of the system, the architecture that supports offer quick test. And as you can see, it's a little bit involved. There are a lot of moving parts. And the reason for that is because the scale at which we're operating. There's not a single process, or it would be infeasible for a single process to ingest the data that we need to process, do all the processing itself, and spit out the testing offers or transitioned offers or passed offers and failed offers. So we need to have some way of splitting up the computation, splitting up the tasks into logical steps. And this diagram kind of outlines what's going on. Although I won't dive into exactly the specifics of this, this top row over here, all the cylinders you see are data stores. These arrows represent the flows of data. Rectangle things, the small rectangles, are Python processes that are used to do a variety of computation. Python processes, you can see the data flowing to other data stores, to other Python processes. This box here, it's hard to see, but eventually the final step of all of the computation that we do is our bidder mechanism, which takes in the new offers that are testing on a website, or the new offers that have failed on a website or passed on the website, and makes bids accordingly. All right, a guest celebrity appearance. All right, so how do we facilitate all of this computation? Whew, all right, tough crowd. How do we facilitate all of this computation? So you saw from the last slide that there are a lot of moving parts, a lot of things that need to be coordinated, a lot of Python processes specifically that need to be coordinated. So to do this at AppNexus, we've implemented distributed work queue. And if you're unfamiliar with distributed work queues, it's, as the name suggests, a way to distribute computation across different machines. And a necessary component in your system if you're doing lots of computation on lots of data. So for our purposes, we're going to call a large unit of work a job. We're going to say that jobs are split into smaller units of work called tasks. It's the job of a scheduler to kick off a job and shard it into many tasks for computation on worker machines. So on the optimization team, we've implemented our own in-house distributed work queue. It uses RabbitMQ to facilitate message passing between workers and schedulers, and between external sources and our scheduler to kick off any sorts of computations that we want to do. So it's very similar to Celery, which is another distributed task thing built in Python that you might be familiar with. Our scheduler begins a job when it receives a notification on the Rabbit Exchange. Besides for spinning off tasks to do the computation, it also stores state information in MySQL. So we always have a global view of exactly what is running and a history of what's run and when. So here's an example of how it fits together. So if you recall, the data pipeline is the part of the larger data flow where data is aggregated from its raw log data form into a more consumable format. So once the data pipeline is done with a specific aggregation, it will send a message to the RabbitMQ exchange, which then routes the message to our scheduler. The scheduler looks at the data source, which has been aggregated, decides whether there are any important jobs or any jobs that the optimization team is interested in that does computation based on this data. If so, it'll spawn off a job, split it into tasks, send those tasks right back over to RabbitMQ where they're distributed across several workers. And the workers do the number crunching, they do the computation, and then store the output into some other data source. So in the case of our offers, in the case of our transitioning offers, this might be the MySQL database from which our bidder reads. So the MySQL database where we store the offer states. It also could be some intermediate cache layer, and it often is, as we'll talk about later. So yeah, that's the work of the workers. I put little doges there because each of the workers runs a watchdog process, but it's much more fun to say watch doge instead of watchdog. Great, so RabbitMQ. Why do we use RabbitMQ and how is it helpful for implementing a distributed work queue? So for our purposes, and these might vary, but for our purposes at AppNexus on the optimization team, we're not interested in really pushing any messaging broker system to the limit. We're really only sending tens of messages per second over the Rabbit Exchange, not millions of messages per second, although it does support that. The thing that we are interested in, and the thing that's important to us, is having flexibility and the power to create semi-complicated rules when sending messages over the exchange. Semi-complicated meaning some messages should be destined for workers, others for schedulers. Some messages should have some priorities. Some messages should or some consumers should only listen to some format of some messages. And really, Rabbit has a lot of flexibility with regard to routing rules that makes it a nice and solid choice for distributed work queue like this. The other important thing that Rabbit does a very good job of is fault tolerance. So it's unacceptable for us to have message failure or any dropped messages, anything like that, because it results in jobs not running or tasks not running, which results in stale or incorrect data. So for example, if we have an offer on a website that is in a testing stage, but it should be failed, it's taking the impressions, it's taking user views that should be allocated to other offers. So wasting impressions, wasting money for the publisher. Also, we use Pika, which is a package used to communicate with Rabbit Exchange, which has fantastic support. It's a Python package. And there are a bunch of other features that make Rabbit pretty ideal for this sort of setup. Great. So now we have an idea of how we carry out computations, how we coordinate computations. So let's talk a little bit more about the data flow, a little more in depth. So this is the data flow a little more in depth. Like I was saying, we start off with all our data in HDFS, where it's later aggregated and stored into Vertica. This green box represents all the sort of the optimization stack where all of our Python processes are running and crunching numbers. The two main components that make up the stack are the caching of data from our Vertica cluster into Redis. We'll go into the specifics later, but this is a very important process for us because there are many processes that are reading or that are using the data that we've aggregated in different and interesting ways. And it's very inefficient to be hitting our Vertica cluster every single time. So we have lots of helper modules that pull out the data, parse it in, and kind of put it into formats that are more useful for the final stage of this process, which is the transitioning of offers from eligible to testing to passed or failed. From there, we store the results into MySQL, and as I was saying, sync it over to bidder memory. And now the bidder knows what should be testing, what are the good offers, what are the bad offers, which ads should I be serving. So HDFS, Hadoop Distributed File System. I'm sure you're all familiar. This is what really accounts for the 100+ terabytes of data a day. This is where it all begins. So HDFS is amazing for very large data sets. It's fault tolerant, which is super important for us. And our particular cluster is composed of 1,400 machines across 2 data centers, one in New York and one in LA. So you are here. The data is now in HDFS. So first step is to aggregate it. So I talked about Vertica, or I mentioned Vertica. Vertica is an HP product. It's a column store database, which means it's very good at performing fast aggregations across columns. Vertica is also horizontally scaling, which is one of the big reasons we use it at AppNexus. We experimented earlier in the early history of AppNexus with other databases for the use case of storing this aggregated form of raw data, and found that a lot of different solutions didn't really scale scale as well as we needed it to. So Vertica supports frequent querying, and our Vertica cluster is composed of about 150 Vertica nodes. All the aggregations are done in Java. And they're supported by the AppNexus data team, which has built a giant infrastructure around pumping data from Hadoop into Vertica in meaningful ways and using complex logic. So we make pretty heavy use of that. So the particular table that stores all of the information that we are interested in for the transitioning of offers on websites. This is the schema for it. As of last check, it was about 332 billion rows of data, which is non-trivial. It has the information that you would expect, which is impression count, so how many views have happened on an offer website combination, how many clicks have happened, and how many conversions, purchases, for example, have happened on this combination. These are the keys to our offer website combinations. We go a little bit more granular into sort of what is an offer, for example, and what is a website, for example. But essentially, these just basically tell that story, and these are the historical stats on those combinations. Great. So we're here now. Our data's in Vertica. It's aggregated in a neat way. It's time to run our army of Python processes that read in this data, do some crunching, do some manipulation, and then cache it. So cache money. All right. So yeah, as I was saying, there's lots of processes that need to access the same aggregated data. And it would be terribly inefficient if all of them had to query Vertica constantly. And like you saw, there's sort of this big synchronization sort of thing that we have to do on the optimization team. So it's honestly just very useful to have an intermediate caching layer where all of these processes or all of the relevant processes can sort of ping and access instead of going to kind of the main source. So how do we do it? What do we use to go from Vertica aggregated data store into caching layer? So we make pretty heavy use of pandas on the optimization team. And pandas, so I'm sure you all are familiar as well, has great support for representing rows and columns in memory via the data frames class. So the API supports really complex row manipulations. And for the most part, we can let pandas worry about performance for the most part, which is nice. And so how we use it is we sort of read it all into memory, or in each of our sort of sharded tasks, we read all this data into memory, do some row manipulation, and then kind of write off the results somewhere else. Under the hood, we use standard PyDBC and IO Pro. If you're unfamiliar with IO Pro, it's a Continuum product who's a sponsor, also a sponsor here at PyData, and just makes memory performance much better for pandas data frames or just pandas objects in general when storing information from external data sources. So here's just a snippet of code. You can see we set up a Vertica connection, and we've built kind of our own API to select data frame. So we do make heavy use of pandas. So examples of things that we cache. So I told you that it's important to cache because there are lots of different processes accessing lots of different data in different ways. So examples of the things that we cache are websites with new data. We don't want to transition offers on websites that don't have new data because there would really be no need to. If an offer is testing on a website, there's no need to do any sort of transitioning, or it would be pointless to continue with any transitioning because it doesn't have data. Another important thing is how many offers should be testing on each website at a time. This is hugely important for our transitioner process because it needs to know, if an offer has failed, for example, how many offers should take its place. Could be one, or perhaps the volume on a website has gone up tenfold since the last time this algorithm ran, and a website with 1 billion impressions per day would obviously need or want maybe more offers testing on it than salsblog.com, which has maybe 10 impressions per day. We also want to know which offers are allowed to serve on which countries or which sizes, because not all ads can serve on all countries or ad sizes. We also want to know how many impressions, clicks, or conversions have happened on a website offer combination. This is the vital sort of information that we need, or that our transitioner needs, because as Stephanie was explaining, after a certain number of impressions, if you haven't got a click on an offer, we consider the offer bad and we scrap it and put it into failed state. So what do we use for caching? Well, we use Redis, which, if you're unfamiliar, is a key value store in memory. The reason we chose Redis at AppNexus is because it has a very rich feature set. It has sets, hash sets, ordered sets, all of which we use in our implementation of this transitioning process. The thing that Redis doesn't have, or maybe one of the complicating factors, is complicating factors of Redis is that it is just a key value store, in that for the most part, you're putting in strings, you're pulling out strings. There's nothing really else going on there. So that on the optimization team, we've sort of built an intermediate layer that sort of puts a model abstraction on top of Redis, which lets us enforce best practices like serialization, deserialization, define namespaces, and lets us treat our interaction with Redis like as if, or it lets us retrieve information from Redis as if they're native Python objects, which is pretty neat. We use Redis Py API. Another Python package has been really great. Oh, beware resource starvation. So this process of pulling from Vertica and caching, or really hitting Vertica, kind of constantly in order to retrieve the most up-to-date data, can really put a strain on our Vertica clusters. And Vertica has a interesting way of dealing with resource management in that it allocates a big chunk of resources for every query that's running on the Vertica cluster. So we noticed that in the process of querying Vertica so frequently, we'd often find that a lot of our queries would fail because of resource starvation. So to prevent that, we use Apache Zookeeper, which is a service that provides distributed synchronization for systems like this. And it was really helpful for sort of mitigating these resource starvation problems that we had. And we use Kazoo, which is a Python package used to interact with Apache Zookeeper. Please help, I'm so hungry, says the resource. Next slide, please. All right, you're here. Redis. So all the data is in Redis. So now it's finally time for our transitioner to run. Data's in a nice form, consumable formats. So all that's left is really to transition into MySQL. So do the final computations. Of course, this is also distributed across many machines. But now the process is much simpler because our data is in a ready state. So now we can take offers. We know exactly how many impressions they got, how many clicks they've got, so we can put them into the appropriate states. Save these states into MySQL, and we do that. We also use SQL Alchemy, which I'm sure a lot of you are familiar with, to do a lot of the writes to MySQL. Here's just an example, some familiar SQL Alchemy syntax using sessions and whatnot. But data's in MySQL now. We can perform the sync to bitter memory and kind of complete this feedback loop. So bitter reads in MySQL, now makes bids according to the offers and the states that those offers are in. Great. So moral of this, there's actually not really a moral, but we needed a nice transition slide to the thank you slide. So it is scale, codes, and math. And really, the big picture and sort of the thing that a lot of you are probably dealing with for whatever you're doing, and the thing that AppNexus deals with on a daily basis is sort of how scale influences the math and the codes of our systems. So this is sort of the holy trinity. It's combining scale, it's combining code, and it's combining math in kind of this beautiful and optimal form to support things that were not possible kind of before. But anyway, if these are the sort of problems that you're interested in, we're hiring. As always, and thank you.
Any questions?
Yeah.
Go ahead.
Process that you mentioned, how often does it repeat?
Yeah, it depends on the particular job that we're running. For the transitioning of offers, for the algorithm that we just discussed, it's twice an hour, so every 30 minutes about. But it depends. It depends on exactly what we're running, because a bunch of jobs have different frequencies. Some are more critical than others, but yeah.
And all the computation happens on the set of offers which is there in your system. So the offers are all like booked in your system, and you have complete knowledge about all the offers.
Yes, yeah. Other questions, concerns? Go ahead.
I guess I was wondering, so with the stage where you load the data to HDFS
Sure.
and then push that data to, I think, Vertica,
Sure.
why would you do the aggregation with an HDFS rather than something like a streaming aggregation where you're keeping track of what it previously was and then just
Yeah, so I mean, we do. So all that, I kind of put a cloud where that happened, which is the data pipeline, which does a bunch of really interesting things, but that is one of the things that it does. Another really cool thing that we support now at AppNexus, and is sort of the direction that we're going down, is not only do we take this data and kind of pump it into an aggregated form in a Vertica database, we also allow any application to read from the stream of data in real time so that they can perform online learning or use it for online learning applications. There's a couple of data scientists in the crowd today that have some experience with that if you're interested, but J Money and Sam, shout out.
When you said that you test out an offer for some time before you actually leave it directly,
Yeah.
you say that you test it out, do you mean that you test it out with a different crowd, or like if it's for the same person, is it like how does that work out?
Oh, so it's not on a user combination. So it's a just website. Well, so it's not actually just a website. It's like a very granular number, like a abstraction of inventory and also a lot of different objects for the buy side. But we're accumulating impressions over time just to test out that offer, not necessarily for a particular user though. So it's like a particular website might happen to have better performance for a particular advertiser. And so we had to slice it that way for the two combinations.
So you're not really like, let's say there's an offer from Macy's, you're not really testing the segment, which segment it is actually hitting the offer. Are you testing that it's hitting the woman or the man, like something like that?
So that's like another layer to this. That it is part of our advertising technology, but I didn't really talk about it here. This particular algorithm doesn't address it, but we have another, like this actual algorithm can be used to address that, but by testing out users. But I mean, it's just like one example of using it. Yep.
I recall the base example that you said for the prior procedure. What was the procedure and prior?
Okay, so I can go back a lot of slides for that. Okay. So you choose a prior, and we just chose something that kind of mimics what a probability distribution for clicks is. So if you take something that like a rare event, like it basically shows that there are very rare events. You could just do that. And oh my gosh, there's so many slides. I'm sorry.
Oh yeah,
Okay.
celebrity.
I wonder if I could have just like minimized this slide and then, we're almost there. Oh, wow. Wow. There's so many slides. Okay, here we go. So is this the question that you had, this one? Basically the prior, you can choose whatever you want here. So you can even take like a uniform distribution. It's not what we did. And then right here, this is just like, we use the probability. So we integrate from the desired probability to a 1, and then we just you update the model using that. Is that what your question was? Like what prior is?
So how do you get those values, those 3 values? How do you get those in the first equation? Right.
This one?
Yeah.
Well, that equation is just a rewriting of this one, because you're saying what's the probability of your actual conversion rate, which you don't know, given 0, and n is the number that you're trying to change over time. So you're just solving for that equation. And p is something that changes because you're integrating from that first initial probability to 1. So that's just a variable. Yep.
You mentioned that you used a more intelligent prior other than just a uniform prior over
Yeah.
possible values. Can you expand on that?
I mean, we use the beta distribution. It was like, I think we used the Jeffreys prior. Yeah. Good.
Question about resource relation. Could you go to the resource relation?
Oh, let's just do this.
No, okay.
Sorry about that.
No problem.
So basically, are you bringing more resources on resource relation automatically, or how do you solve that problem?
So it was, the resource starvation problem was rooted in sort of a synchronization problem, which is that we would often find a lot of processes just querying Vertica at the same time.
So you basically have contention.
Yes.
And,
Yeah.
And how does Kazoo resolves contention? Sorry, I'm not familiar with Kazoo.
Sure. So it's actually Apache Zookeeper that just allows us to have a synchronization mechanism that supports our sort of distributed system. Because there's no way for these processes to interact with each other, or I mean, there are, but the way that they sort of like tell each other who should be accessing Vertica or who shouldn't be accessing Vertica or who should be waiting for Vertica access is through Apache Zookeeper. So
Zookeeper does the synchronization.
Zookeeper does synchronization, exactly.
Thank you.
Yeah, thank you. Oh,
All right.
sure. All right, thanks guys. Come
Thanks.
talk to us about jobs.